Hello, everyone. Welcome back to Innovashinka, your hub for deep dives into the world of machine learning. In our previous sessions, we've covered foundational topics like supervised learning, linear regression, and model evaluation. We've also explored the cost function, which plays a key role in evaluating how well our model is performing. But this brings us to the next critical question. How do we actually minimize the cost function to improve our model's predictions? That's where gradient descent steps in. Have you ever wondered how a model fine-tunes its parameters to make better predictions? Today we'll explore what gradient descent is, how it helps us optimize our model, and why it's essential for minimizing errors. Let's get started. Gradient descent is an optimization algorithm used in machine learning and deep learning to minimize the cost function, which measures how well a model's predictions match the actual data. The goal of gradient descent is to adjust the model's parameters, like weights and biases, in such a way that the cost function is minimized, leading to a more accurate model. The process involves calculating the gradient or slope of the cost function at a given point and then updating the parameters in the opposite direction of the gradient to reduce the error. The learning rate controls how big each step should be. If the learning rate is too high, the algorithm might overshoot the minimum, and if it's too low, the algorithm will take too long to converge. Gradient descent iterates this process until the cost function reaches its lowest point, indicating that the model has been optimized. In practical terms, gradient descent is widely used in training models for regression, classification, and neural networks, making it a fundamental concept in machine learning. Weights are the parameters, often represented as m, that determine the influence of input features on the model's predictions, while biases, represented as b, are the constants added to the output to adjust the predictions independently of the input values. Now that we've established the foundational principles of gradient descent, it's time to delve into its significance in the field of machine learning. Gradient descent is more than just an optimization technique. It serves as the core framework for many machine learning models, allowing them to learn from data effectively. By making iterative adjustments to weights and biases, gradient descent works to minimize the cost function, thereby enhancing the model's predictions. But what makes this process so essential? Let's explore the key reasons that underscore the importance of gradient descent in creating robust and accurate machine learning models. Understanding the significance of gradient descent is vital for anyone entering the realm of machine learning. First and foremost, it acts as a fundamental optimization method that enables models to learn from data by refining parameters to reduce error. This optimization process is crucial for achieving precise predictions. Gradient descent stands out for its efficiency, providing a computationally viable approach to converge toward optimal parameter values, which is particularly beneficial when dealing with large datasets and intricate models. Additionally, the adaptability of gradient descent allows for its application across various machine learning algorithms and cost functions, enhancing its effectiveness in multiple scenarios. It also lays the groundwork for more advanced optimization techniques such as stochastic gradient descent (SGD) and mini-batch gradient descent, which further boost convergence speed and model performance. The influence of gradient descent on model performance is profound. The careful adjustment of parameters, such as the learning rate, directly affects the convergence rate and overall accuracy of the model. Furthermore, gradient descent is proficient at managing nonlinear models, enabling the identification of complex patterns in the data. Overall, gradient descent is an indispensable tool for machine learning practitioners, driving the optimization of models and improving their predictive abilities. Now, let's explore the concept of gradients, which are fundamental to the workings of gradient descent. Gradients can be understood as mathematical vectors that indicate the direction and rate of change of a function with respect to its parameters. Specifically, in the context of optimization, gradients reveal how the cost function changes as we modify the weights and biases of our model. This is crucial because during the gradient descent process, we need to know in which direction to adjust our parameters to effectively minimize the cost function. To calculate these gradients, we rely on derivatives, which provide us with the slope of the cost function at any given point. The slope tells us how steeply the function is rising or falling, allowing us to determine the necessary adjustments to our parameters. A key element in this process is the learning rate, a hyperparameter that dictates the size of the steps we take along the gradient during each iteration. A well-chosen learning rate ensures that we make effective progress toward the minimum without overshooting and potentially diverging from our target. Moreover, the magnitude of the gradient itself plays a significant role in our optimization journey. When the gradient is large, it indicates a steep slope, which prompts larger updates to the weights and biases, thereby accelerating our convergence toward the minimum. Conversely, a smaller gradient results in smaller updates, which can slow down the learning process. Understanding gradients not only equips us with the necessary tools to implement gradient descent effectively, but also enhances our ability to optimize machine learning models efficiently. Grasping this concept is essential for anyone looking to deepen their knowledge of machine learning algorithms and their underlying mechanics. In our last session, we explored a practical example dealing with the cost function, where we observed how changing the weight value W significantly impacted the mean squared error MSE. If you haven't seen that video yet, I highly recommend checking it out first, as it will help you understand this session better. You can find the link in the I section above. The values of W we used were as follows, and correspondingly we calculated the MSE values. Now, let's plot the graph to visualize the relationship between MSE and W. As we plot these values, we can see the data points marked on the graph, where each point represents a specific pair of W and its respective MSE. To better understand this, we'll plot some key pairs of W and their corresponding MSE values for a clearer representation. Once we connect these points with a line, we notice that the graph forms a parabolic shape. This parabolic curve is crucial because the lowest point on the graph, at W equals 0.2, represents the minimum MSE. This minimum is vital for our model's performance, as it indicates the optimal weight at which the cost function is minimized, leading to the best predictions. At this point, the model has adjusted its parameters to ensure the error between the predicted and actual values is as small as possible, improving overall accuracy. So now what we have seen that is how changing the values of W manually affected the mean squared error, MSE. We were adjusting these values to see how the model's error changed with each adjustment. However, in real machine learning algorithms, we often don't know the best value for W upfront. This is where the concept of the gradient descent algorithm comes into play. Instead of manually guessing the values of W, gradient descent helps us find the optimal value for W automatically by minimizing the MSE. It doesn't just work for a single weight either. It can handle multiple weights like W1, W2, W3 till Wn, and even the bias term B, which is common in multiple linear regression. The beauty of gradient descent is that it enables us to efficiently optimize these parameters all at once, even when we are working with complex models. Now, let's see how gradient descent helps find the minimum MSE. To minimize the MSE and find the best weights, gradient descent uses the following formula to update the weights step by step. New weight equals current weight, learning rate times derivative of the cost function with respect to the weight. Here, W is the weight we are optimizing. A is the learning rate that controls how big of a step we take, and derivative of the cost function with respect to the weight is the gradient or slope of the cost function. The learning rate, commonly represented as alpha, is a vital hyperparameter in the gradient descent algorithm that significantly influences the training process of machine learning models. It dictates the size of the steps taken towards the minimum of the cost function during optimization. A small learning rate may lead to slow convergence, making the model require more iterations to reach the optimal solution. This sluggishness can be particularly problematic with large datasets, where time efficiency becomes a concern. On the other hand, if the learning rate is set too high, the algorithm may overshoot the minimum, leading to divergence or oscillation around the optimal point rather than settling down. Striking the right balance for the learning rate is crucial for efficient training, as it helps achieve a good compromise between speed and stability. Various strategies, such as learning rate schedules, which adjust the learning rate dynamically during training, or adaptive learning rates that change based on the model's performance, can aid in fine-tuning this important parameter, thereby enhancing the model's learning efficiency. To visualize the concept of the learning rate in the context of gradient descent, imagine a graph where the x-axis represents the weight values W that we are trying to optimize, and the y-axis represents the cost function values, such as mean squared error, MSE. This graph serves as a landscape where we want to find the lowest point, essentially the optimal weight value that minimizes our cost function. When we set a high learning rate, the algorithm makes large updates to the weight values in each iteration. This aggressive approach can result in the algorithm overshooting the minimum point of the cost function, leading to a zigzagging path across the graph. Instead of gradually descending towards the minimum, the updates may cause the model to bounce back and forth across the optimal point, which can prevent convergence altogether. As a result, the algorithm may oscillate indefinitely without settling at a solution, making it ineffective in minimizing the cost function. On the other hand, if we set the learning rate too low, the model will take very small steps towards the minimum. While this may seem safe, it has its own drawbacks. The tiny updates mean that the training process will take significantly longer to reach the optimal weight values. Moreover, there's a risk that the model may get stuck in local minima, points where the cost function is lower than surrounding areas, but not necessarily the lowest point overall. This stagnation can severely hinder the model's performance and prevent it from achieving optimal accuracy. Finding the right balance in setting the learning rate is crucial for effective training in gradient descent. An optimal learning rate allows the algorithm to make sufficiently large updates that move it towards the minimum quickly, while still being small enough to avoid overshooting. This balance is essential for ensuring that the model learns efficiently from the data and converges to the best possible solution. Through careful tuning of the learning rate, we can significantly enhance the performance and convergence speed of our machine learning models, making this hyperparameter a critical focus in the training process. In today's session, we delved into the core of gradient descent, an essential optimization algorithm in machine learning. We began by revisiting how it iteratively adjusts weights and biases to minimize the cost function, highlighting its application in both single and multiple linear regression models where several weights and biases are involved. We introduced the gradient descent algorithm formula, demonstrating how partial derivatives are used to calculate gradients, which guide the model in updating its parameters step by step. This process is crucial for finding the optimal weight values that reduce the cost function and improve the model's accuracy. We also explored the significance of the learning rate, which controls the size of each step taken during weight adjustments. A high learning rate can cause the model to overshoot the minimum, while a low rate may result in slow progress or getting stuck in local minima. Visualizing these effects helped us understand why tuning the learning rate is so critical for efficient training. We've covered some complex topics today, and if anything is unclear, I encourage you to revisit the session for better understanding. Feel free to ask any questions or share your doubts in the comments, and I'll be happy to clarify them. In the next session, we will continue exploring how gradient descent algorithms adapt to different learning rates and more advanced concepts like learning rate schedules. Stay tuned and don't forget to like, share, and subscribe.